Oh, hello. Good morning. It's Dr. Jeff Holm, and this is the pre-recorded lecture for time value of money. And today's topic is um, how to solve for n in a single cash flow model. So, in our last class, we discussed how to solve for the rate from the base compounding model for future value, right? Um, so there can be, in this base model, there can be four possible questions that can arise from this model. First, the obvious one is uh, when the future value is the unknown, and we know then it's principal times 1 plus r raised to n. Now, the second possible question is when the principal is the unknown. If the principal is the unknown, we need to solve this equation for principal. That means um, future value is known, rate is known, n, the time periods, number of periods, or number of compounding periods are known, and the principal is the unknown. When the principal is the unknown, that is also called the present value, because if you solve for that principal, then how do we solve for that? We discussed it. All equations, no matter how complicated it may look, or they may look, they can be solved if you identify that z equals x times y structure. And this base formula already lends itself to that structure. As you can see, you can consider this as x. This is, z, and principal as x, and this chunk as y. And then since x is our unknown, and you would solve for that by z divided by y, by dividing z by y. Also, principal can be solved by dividing fv, future value, by 1 plus r raised to n. Now, so another scenario, another possible question that can arise from that is, of course, what should be the rate? Of course, we discussed it in the last class, so we're not going to talk about it in detail. But basically, it's a conceivable question. You have $10,000 today, and you're in 3 years, you want to grow it into $50,000. So then the relevant question is, what should be the rate, right? And just like that, n can be the unknown. In other words, another conceivable question is, you have $10,000 today, and the prevailing market interest rate is 10%, and you want to grow it to $50,000, then the relevant question would be, how many years will it take, right? So that is a fourth question that can arise from this base formula, or this compounding equation, right? So basically, I'm showing you the formula and the steps of derivation here. But as I said, to identify that z equals x times y structure, you will have to simplify the formula to the best that you can. So our unknown is n. Now this is a problem. We can't isolate n immediately or directly because n is an exponent. And how do you solve for an exponent? So anyway, we will need to isolate this term, 1 plus r raised to n, because we cannot get to n directly. We'll have to get to whatever you can. So first, I would isolate this term. So then, in the left-hand side will be FV over PV. In the right-hand side, I have isolated 1 plus r raised to n. And then suddenly you notice that it makes a jump. You see ln of FV over PV in the left-hand side, and on the right-hand side, you see ln of 1 plus r raised to n. Now suddenly, what is ln? ln stands for natural log. Now the question is, what is natural log then? Well, you understand what logarithm is, and if you're not familiar with it, let's get to the basics, right, of logarithm. So I will need to change, switch from this PowerPoint to whiteboard. So let me give me some time to transition, right? Stop sharing this PowerPoint, and I'm gonna go into, let me use whiteboard, okay? All righty. Okay, so let me, let's see if I can, okay. So we all know what, basically know what, oh, I will have to use this pencil, okay? Okay. Oh, I will use blue. Blue's fine. Okay. So we all know 100 is 10 squared. This is not easy to, and 1,000 is 10 to the third power. And if we keep going, we can do it like this. I mean, even if it is, 1 million, commas, right? Actually, I should have put comma there too. 10 to the sixth. And then what is 1 billion? 1 billion is 10 to the ninth, because, 1 billion is 1,000 million, right? Now, these large numbers are very cumbersome, because putting zeros, zeros already, so many zeros, that's already very exhausting and annoying, right? But there's a better way of representing them by the exponent, right? So powers of 10, 10 squared, 10 cubed, 10 to the sixth power, 10 to the ninth power, and all these things called the power function, right? Or the powers of 10 in this case, would nicely make the numbers compact, right? Now, there's another way of expressing it. We can use log, which means, log of 100 to base 10. We know that means we're taking, we want to express this 100 by only the exponent of 10, right? So that means, again, I can write it as log of 10 squared to base 10. Okay? And then this can be written as 2, meaning when you take the log of 10 squared to base 10, you can express that number, you can express that only by the exponent. But how is this possible? Well, because when you write in log, if I can rewrite it as, okay, this, I will extend this equal sign here. If you rewrite it, it's like two times log of 10 to base 10. In other words, the exponent can be brought down like a multiplicative term. Why? This is possible because what is log of 10 to base 10? What do you think it is? Log of 10 to base 10 is simply 1. Isn't that right? That will be simply 1, right? This number, because it's 10 to itself, right? It's 10 raised to 1, and then it, 10 raised to 1 is itself, right? Log of 10 to base 10 means simply 10 to 1. So because log is basically a way of expressing a number as an exponent to the base, so this term becomes 1, I'm sorry, and then times 2, so that becomes 2, right? And likewise, 1000 can be expressed as log of 10 cubed to base 10, and by the same procedure, it simply turns into 3. And then what about this? 1 million will be 6, and 1 billion will be 9. In other words, all these exponents can be used to compactly to express these large quantity in a more manageable and compact way, right? Now, and it's this properties that of log, in other words, when you have log of x raised to y, of course, we assume that the base is x, right? Base has to be x. Then you can write it as y times log of x, right? And what does this mean? This is a multiplicative, right? This is a multiplicative structure. In other words, we turned power function structure into a multiplicative structure. Now you remember what this means? What is, how this can help us? If you guys are okay, I'm gonna erase all this. Okay, so remember we had a structure z equals x raised to y. That was the structure we had, remember? Well, I cannot go back to, at this point, to PowerPoint. I will have to switch the screen, and it's gonna, disrupt everything. So just remember that to solve for n, we had to do, remember, FV. We had to isolate n, but since there is no way you can isolate directly n, you had to isolate whatever you could. And it was like this, right? So think about it. What is this? This is exactly z equals x raised to y structure, right? You see the parallel in structure here. This is z, this is x, this is raised y. But then think about it. All equations can be solved if you identify that x times y structure, right? That was why we were trying to reduce this to the simplest form. But then we got stuck because it was like this. The structure was this, not this. But then we also learned that if you we just saw that if you take log of x, right, raised to y, then it can be rewritten as y times log of x, right? So we found that we can convert this power function structure into x times y structure, right? So then our question is, okay, so that means, we can transform this into log of z equals log of x raised to y. Now, you'll have to take the log on the left-hand side as well, because if you take the log on the right-hand side, whatever you do to the right-hand side or one side of the equation, you must do the same to the other side of the equation. Otherwise, this equality won't hold. Okay? So then this can be rewritten as, we all know that it is y times log of x. Now, what does it look like? The left-hand side is still this. This is the left-hand side, right? And this is the right-hand side. And the right-hand side is now, the left and the right-hand side is now z equals y times x times y structure, right? Log z equals to y times log of x. So then what do you do? Because y is our unknown, and that's what you want to solve for, then you can simply divide the left-hand side, log of z, by the right-hand side, which is log of x, right? And the problem solved. So this way, in other words, this is n, right? And if you take the log of the left-hand side, take the log of the right-hand side, right? You'll be able to find n. Now, then our next question. Our next question is then, can we use, then, let's get back to common log. So let me erase this. Let me get back to common log. The log we understand, the log we know up to this point is the log using 10 as the base, right? Right? Like, log of 10 to nth power to base 10. And this is called common log, right? There are largely three types of logs: common log and binary log. Binary log is log using 2 as the base. So in binary log, then think about it. 4 is 2 squared, so it's going to be 2. And 8 is 2 to the third power, so log of 8 to base 2 will be 3, and so on. And then natural log. Natural log is a log using e, or Euler's number, as the base. That e is called Euler's number. Now, some people pronounce it as Euler, but that's not right, because Euler was a German mathematician in the around 17th century, and two of the big names in math, two of the big names that gave birth to modern math are Euler and Gauss. There are other, great names like Laplace, Lagrange, who are French, but Euler and Gauss are German mathematicians, or Swiss German. And in honor of his heritage, it's not pronounced Euler, it's pronounced Euler. So it's not anglicized. Not everything needs to be anglicized. But anyway, our next question is then, what is Euler's number, and how does that allow, or how does that enable natural log? Okay, so to answer that question, we will have to switch back to the PowerPoint. So let me switch back, and then okay. And let me go back to, let me go to, okay, so, oh, there it is. Let me move this around. And the volume might be You might need to, the volume on the video may not be quite um, audible. I mean, you may not hear the volume on the video. I will provide, there is, I have already provided link to this video in the temporary folder. So if you don't hear the audio on this video, right? Please uh, visit the temporary folder and you will find the link. Okay. All right. Here we go.
The two most common logarithms used are log to the base 10 and log to the base 8. Why are they the most common logarithms? How do you understand that? Log to the base 10 log 100 to the base 10 is 2. 1000 to the base 10 is 3. Has been found as minuscule of maximum number. But log to the base 8 is what I'm deeply interested in. It's for the amplifier. And it almost has any. Log to the base 8 is almost has any. So log tries to the base 8 must try any. What does this mean? Some call it a maximum number. Some call it an irrational constant. Some call it an Euler's number. But the harsh truth is this: very few people actually understand what E is. To get to E, we first need to understand rules. Let's say a particular rate doubles every time you move. On this timeline, this is play, and every second is one time you move. Assume you have a time piece. At the end of the move, and in this second period, 2 times 5 is the number of times. And at the end of the third period, we'll have 8 times. How do we do that? First, we see that the value at the end of the time periods are constant. It is the log 2 to the power n, where n is the large complex number. 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on. This is one way to illustrate the dead double rule. Another way to look at it is that there should be 100% of movement every time we move. 1 plus 100% of 1 is 0. 1 divided by 0 is 1 over 100%, 2 over 2. If you multiply 2 dollars into 2 dollars, you get 100% of 2 makes a square, and so on. So doubling the value is the same as the 100% of 3. So 2 raised to n is nothing but 1 plus 100% of 3. Similarly, we see 100% of 1 times 4 is 4. Here, this is a large number. We want to assume that the number is continuous over time. We are assuming this is double. Every time we move the value, we are basically assuming we have to see what that means. The more we understand rules, the more we understand. Every year, more and more people understand rules. They actually realize what even the hardest ones do. Look at the exactly for example. When we started, we used to get around 30 minutes a day. And after a year, we started getting around 40 minutes a day. It doesn't seem like the hardest work in the world. We just actually love it. So now we know what it is. What do we do? We understand how to move the data. We see that no matter how many times we move it 100% every time, we always see the exact same value. We just have to write it as minus 1 or minus 2. And the only thing we have to do is simply multiply it. We have to multiply it by 4. Looks like 20. Let's divide the year into 2 equal parts, 6 months and 6 then we have the dollar that we got, the original dollar name, and we also have the 25 cents from these 50 cents mint. A total of $2.25. This is very intelligent. We can also understand this as a formula, which would be 1 plus 1 is less than 2, the whole square. We have the math to square root of 2. This is very simple. We have divided 1 year into 4 quarters. This is how we do it. Looks messy, but it's actually very simple if you've understood the concept. It's 20% growth in the quarter. This math takes 2. What is 100% of your pay? It always very low. We would approximately get $2.441 at the end of the first year. As the total cost of it, and understanding monthly growth diagram means that the 100% is number 1. If 2 times is equal to
Alrighty. Here, the video, in this video, fairly important concepts are introduced. One is the discrete time and continuous time, right? As you saw in the example of the boy growing, in nature, nothing grows in discrete or in discontinuous fashion, right? The growth happens gradually and continuously. Everything grows that way, right? It doesn't grow at the growth doesn't happen just instantaneously at the end of the year or at a strike of a clock. Now, also, if you think about it, the time we understand the nature of time. We understand time as minutes, hours, seconds, days, weeks, months, years, and these are all discrete units, right? Discrete units. But think about it. Time never declared itself in a discrete unit. It's all a result of human intervention. Isn't it right? Time just flows quietly without saying anything, right? Time just flows smoothly and seamlessly and continuously, right? Without making any announcement like, it's 1 minute, it's this, 2 minutes, right? So time by itself is continuous. And then and since the growth is continuous, how do we capture that smooth continuity or the smooth fluidity of that growth over time? Well, think about it. The best thing we can do is by splitting time into smaller fragments, right? Just like this. At first, the 1 year was split into half years, right? And then in the next, the 1 year is split into 4 quarters. And as we continue to do this, let's say, 1 year is 365 days, right? And then 24 hours times 365 will express 1 year in hours. Times 60, that times 60 will express 1 year in minutes. And that times 60 will again express 1 year in seconds, right? And what is smaller segment? What is smaller unit than second? 1/10 of a second, 1/100th of a second. Have you ever heard of nanosecond? What's a nanosecond? Nanosecond is a 1 over 1 billion. In other words, 1 billionth of a second, or is called, also 1 to the negative 9. 1 to the negative 9 power, right? Negative, you remember x to the negative 1 means 1 over x. It means reciprocal, right? So x to the negative 2 is 1 over x squared. So nanosecond means, nano means ninth, right? Therefore, if you split time, I mean, how finely, how infinitely fine fragments can we break the time up? There is no limit, right? There can be even, 1 billionth of a 1 billionth of a second. But then, because there's no limit to that, it's a futile effort to try to break it up like that. So let's continue with the video, and in the next segment, it will give you the example. All right. Another thing, the n this use here is actually in our model m. Remember the compounding frequency per year, m, right? Now, so and our n is the result of m times t, the number of years. I mean, they can use n as the number of compounding frequency, a compounding frequency, or number of compounding per year, because they have only 1 year timeline. But if you have multiple year timeline, we need to distinguish between n and m, right? But anyway, if you understand, as long as you understand, this is the notation we have been using is m, then that's fine. So let's continue. All right. Well, here, see, in this video, they experiment. They experiment with, a large number of n. In other words, that means you are splitting this interest rate, right? Annual interest rate. I mean, this can be 1 or any number, right? Because if the growth rate is 1, that means 100% growth. But it does. We can keep it there for now because it can be replaced by like 5% or 10%, which would be 0.05 or 0.1. But the idea is when if the compounding frequency increases, right? That means the denominator increases and the exponent increases. And then as it happens, what's going to be the result of this compounding, right? And then do we need to go, they stopped at 1 million, but you can try, 10 million, 100 million, 1 billion, but there's no point in doing that because anyway, eventually it doesn't grow much more than this. The result of the compounding will all converge to something around 2.71828 or something like that. So, in other words, this is the ultimate result of this compounding in the limit, right? So that is what E is. That's what the Euler's number is, which is called irrational constant. Irrational meaning there can be no exact ratio, right? An exact ratio would be like 2.7 if it stops there, right? Then it's rational, meaning there's a definitive ratio. But the numbers like 3.14 pi or Euler's number, these are irrational, meaning they keep on going forever. Okay, so instead of writing it in number, we simply write it as E. Okay, so that's what Euler's number is, and that is going to be the base of natural law. Now, to explain more about the natural law, we will have to do it in the second part of the video. It's been almost 50 minutes, I believe, so we'll have to pause the video here and take a break, and then I'll see I'll see you again in the part 2 of this video. Okay, thank you. See you soon.